Welcome. In this module, we will start our discussion on geometric synthesis or physical design. Geometric synthesis or physical design comes after the logic synthesis step. At the end of the logic synthesis and technology mapping step, we have a detailed circuit diagram of the chip, of the functionality that we want to implement in terms of cells, macros, gates and transistors that will be used in the design and their interconnections. At the beginning of the physical design step, this circuit diagram is usually represented as a data structure called netlist. Netlist is a graph-like structure in which the nodes are the modules, that is the cells, macros, transistors, gates that we just mentioned, and the edges are the interconnections. So the edges will be, if two cells are connected via wires, there will be an interconnection between these two modules, and this will be represented in the netlist as an edge. So what is the physical design process? Given this netlist, to obtain a geometrical layout. The process of converting the specification of an electrical circuit called netlist into a geometric representation called layout. The diagram that we have shown below is an example of a layout. On this layout, we express here the floor of a chip. The entire blue square box is the floor of the chip. On the periphery of the chip, we see terminals and there are blocks. These rectangular boxes that are shown in this diagram are the circuit blocks. We are also seeing here that these circuit blocks are connected through wires. So the chip area will be covered by three main types of components. One are the terminals here seen, which takes very less space. The blocks, that is the circuit blocks themselves, the logic block, and we need area for interconnection between the blocks. So the physical design process is very complicated because the circuit diagram form from which we have to obtain the final geometric layout can be very huge, consisting of millions of transistors interconnected in very complex ways. And we have to obtain an optimized layout which tries to minimize the chip area, say, could be minimizing the critical length of a wire in the whole design, in the need to maximize performance in the face of constraints such as limited area, number of metal layers or routing layers available, etc. And hence the whole physical design process has been divided into a set of stages or steps. The first step is partitioning. In the partitioning process, we partition the entire big circuit diagram that we have into controllable sub-circuits or sub-partitions. This circuit here has been divided into three partitions using two cut lines, cut line 1 and cut line 2. And we have three partitions, partition 1, partition 2 and partition 3. After the partitioning process, each of these partitions will be called a block, and there will be interconnections among blocks. So each block will have a specific geometric properties, because in this block we will now have a fairly good idea of what are the components in these blocks, how are they interconnected. So we will get an approximate size and shape of each block as well at the output of the partitioning process. So hence at the output of the partitioning process we will have blocks along with their interconnections. Now these blocks have to be placed on the floor of the chip. This is done in two steps, floor planning and placement. In the floor planning step, we place the blocks such that no two blocks overlap, and the area of the whole chip after their placement on the floor can be minimized. We also want to minimize the total routing area required as well. So after the floor planning step, we come to the placement step, where we find the exact coordinates of the blocks on the floor of the chip. In the floor planning phase, we only obtain a relative order of placement of the blocks on the floor of the chip. We don't get the exact coordinates for each block. At the placement phase, we obtain the exact coordinates of each block. In the routing phase, what we do is we obtain for each wire connecting the blocks a set of areas through which it will be interconnected. So, we have areas between the blocks. The vacant spaces within the blocks will be divided into structures called channels and switch boxes, and we have to route each wire, each interconnection between every two blocks through these vacant spaces, and also over the top of the blocks, and connect these blocks. This is done in the routing phase. In the compaction phase, what we do is to reduce the size of the entire circuit to obtain. Now, before going into the algorithms, we need to understand how do we represent and manipulate a layout through the design process. So, the layout is manipulated through a CAD tool called layout editor. So, layout editor is a CAD tool that allows a human designer to create and edit VLSI layouts. So, what do we have in a layout? A layout contains a collection of tiles. A tile is a rectangular section within a single layer. Tiles are not allowed to overlap within a layer. So, within a given layer, I cannot overlap two tiles. The elements of a layout are referred to as block tiles. So, we will have block tiles and vacant tiles. The blocks in the circuit will be represented as block tiles. The vacant spaces will be represented as vacant tiles. The area of the layout that does not contain a block is referred to as the vacant space. The vacant space can be partitioned into a series of vacant tiles. So, here we represent an example. We have three circuit blocks A, B and C, and we have this vacant space here. Now, here we have also divided the vacant space into tiles. So, these are vacant tiles, these will be vacant tiles, and these are block tiles, right. The vacant space is also partitioned into vacant tiles. Now, given this layout editor, we also require data structures to represent the layout. So, that is done using the corner stitching data structure. There are other legacy data structures, but the most important data structure that is used today is the corner stitching data structure, and hence we will discuss this data structure here. In the corner stitching data structure, a floor with some solid tiles or blocks are given to me. Then we partition the floor with the maximal number of horizontal strips to define blank or vacant tiles. So, at the beginning we are only given a vacant space with blocks on that, and then we have to divide the vacant space into maximal horizontal strips. For each tile we have to store its position, size description and other attributes, and then we insert corner stitches, pointers 4 per tile for both solid and vacant tiles, pointing to appropriate neighboring tiles. If this one is a tile, it has 4 pointers: RT pointer, right top, top right, bottom left and left bottom. These 4 pointers point to 4 tiles which are neighboring to it, right. And this is an example as to how the whole layout will be represented through the corner stitching data structure. We see that each tile is stitched to the tiles neighboring to it, right, through the pointers that we have here. Now, after we have defined the data structures, we need to also have operations to operate on these data structures. So, what are the atomic operations that can be performed on layout editors? The basic set of operations that give a designer the freedom to fully manipulate a layout are called the atomic operations. So, we are now discussing operations that can be used on the layout editors. The algorithms will use these operations to manipulate the layout. So, point finding: given the coordinates of a point Pxy, determine whether P lies within a block, and if so, identify that block. Neighbor finding, determine all blocks touching a given block B. So that means if I have a block, there can be many other blocks that is touching its boundaries. So this function will allow us to find all the tiles that are neighboring to this block B. Block visibility, determine all blocks visible in x and y directions from a given block B. Area search, given a fixed area A defined by its upper left corner, its length L and width W, determine the blocks with which A intersect. So we have a tile which has a fixed location on the floor of the chip, right? Its upper left corner is defined by the coordinates x comma y. We also know the length of the chip and the width of the chip. So now this operation will allow us to determine all blocks with which A intersect, with which A overlap. Directed area enumeration, given a fixed area A, visit each block intersecting A exactly once in a sorted order. So whoever is intersecting A, we will visit that block intersecting A exactly once in a sorted order. Block insertion, insert a new block such that it does not intersect with any existing block. Block deletion, remove a block B from the layout. Plowing, given an area A and direction D, remove all blocks BI from A by shifting them in direction D while preserving their order. So we are given an area A on the floor of the chip, and we are also given a direction D, say right, left, etc. So we have to remove all blocks from this area A in the direction D, such that we have to keep the order of the blocks that were previously there. We cannot change the order of the blocks on the layout. The order of the blocks on the layout should remain same, but we have to remove all blocks BI by shifting them in the direction D. Compaction, plowing or compressing the entire layout is called compaction. Channel generation, determining vacant space in the layout and partitioning into tiles. With this we come to the end of this module.